Okay, so the first thing we need to talk about for this installment of flip notes is the states of matter. There's three: solid, liquid, gas. When you were balancing equations, we saw there was an S, an L, or a G. That's what those stand for: solid, liquid, or gas. Solids have a fixed volume and a fixed shape. So I want you to think about if you have a rock or something that's solid, a sneaker even is a solid. You have a fixed volume and a fixed shape. If you put that sneaker in a bucket, it doesn't change the shape of the sneaker. It stays being a sneaker. Same with a rock. If you put a rock in a big container, it doesn't break down and fill the container. That's something a liquid does. Liquids have a fixed volume, but their shape changes based on the container. So if I have a graduated cylinder and I have 5 milliliters of, let's say, water, and I pour this into a lower with a larger base, different shape container, the water is still 5 milliliters. We didn't change the volume, except it's going to be a lot lower. If this is, say, 3 inches, now it's only 1 inch. So that's what changing the shape based on the container is referring to. Gases do this as well, but their particles move the most rapidly when you're looking at in comparison to a solid and a liquid. So if I have a gas and it's in a container, all these particles or the molecules, they're moving around, but they're not really attracted to each other. And again, the volume changes based on the container. So if I have a container this big versus if I have a container this big, I could fit all of these molecules of gas in there. They're just going to be tighter together. And that would then change the pressure, but that's not something you guys need to know. You do need to know, however, that to change the state, so to go from a solid to a liquid or a liquid to a gas, you need to have thermal energy. And now we're going to talk a little bit about energy and then relate that to chemical reactions. So we just said thermal, but there are different types of energy. And this is important because the amount of energy in the universe stays the same, or you could say it's constant. Now if you think about this, you need energy to do everything. To chew your gum, to take notes, to go up the steps, to eat. Everything you do, same as chemical reactions, every chemical reaction needs some amount of energy. But the energy is always constant. So then where do they get it from? The answer to that is energy comes in different types of forms. So there's multiple forms of energy. And you cannot create energy, but you can transfer it from one type to another. So you can switch energy. So we had thermal on the previous slide. There's chemical energy, electrical energy, radiant energy, which is the energy from light, mechanical, you could think solar, wind, water, all these things are different types of energy. The atoms and molecules are constantly moving, so in the solid and the liquid and the gas, but the space and the amount they're moving, or the speed, is what determines what state they're in. When we look at chemical reactions, there is a conservation of mass. So we looked at conservation of energy. Now there's a conservation of matter. So matter cannot be created or destroyed, just like energy cannot be created or destroyed. This is why we need to balance equations. So when you're looking at a chemical reaction, you have one substance and it's changing into another substance. So you have the reactants and they're turning into the products. Energy is absorbed and released when you break those bonds and when you form new ones. But again, the number of atoms has to be the same before with the reactants and after with the products. And again, this is why we have to balance equations. When we're looking at chemical reactions, that's chemistry. The amount of chemical reactions that happen in a body or in an organism is metabolism. So when you're describing all of the chemical reactions that occur in an organism, you call that metabolism. And there's different types of chemical reactions. The first kind you guys need to know is synthesis. So when we looked at the viruses and they were synthesizing the parts, they were being put together in the cell. Synthesis as a chemical reaction, same thing. We have A and we're adding it to B, and then we have a new product, A and B. Decomposition, think like a tree is decomposing. What does that mean? It means it's breaking down. So we have A and B on the reactants, they're together. We're decomposing them, and they're breaking down into A plus B. Exchange, on the worksheet we did, this is also called synthesis. So we have A and B and C. Notice A and B are together and C is by itself. We're going to exchange one of these. So this is a single exchange or a single displacement. So A and B, when we look over on the product side, A is now with C. So B and C were exchanged so that A and C are bonded together now and B is by itself. So the important thing there is we have the thing by itself is different on the product side than it is on the reactant side. When we look at this last one here, it's a double displacement or a double exchange. So we're exchanging two things. So we have A and B again, but now we introduced a D that's bonded to C on the reactant side. When we go over here to the products, A is now with C and B is now with D. So we exchanged what both things were bonded to. There's also something called redox reactions, and this is drawn on. I'm going to go over that. So a redox reaction is kind of like an umbrella term, and redox right here stands for oxidation reduction reaction. They have a transfer of electrons, and I have an arrow drawn to reaction here because this RxN is just shorthand for reaction. This is the same thing as if you write e to the minus for electrons. I just wanted you guys to see that and have experience that you know what that means. Oxidation reduction reactions or redox reactions have two parts. There's an oxidation reaction and a reduction reaction. The oxidation reaction, the reactant is losing electrons. So if you're losing negativity, you're actually becoming more positive. Reduction reactions are the opposite of this. That is the reactant gains electrons, so they're becoming more positive. If you're gaining negative particles, you're becoming more positive. And these are just some ways for you to remember this. Oil rig is the most common one, and the oil is oxidation is lost, and the rig is reduction is gained. You can also look at Leo the lion says grr. You may think this is silly. You totally do not have to use this. But I like this because, see I circled the E's here? This tells you what you're losing. So losing electrons is oxidation, that's the Leo, and the grr is gaining electrons is reduction. Up to you, you don't even need to use either of those. But the important thing for you to take away from this is that redox reactions always occur together. So the electron given up by the oxidation is gained by another substance in the reduction reaction. So again, we talked about conservation of energy, conservation of matter. Right now we have conservation of electrons. So if nothing gives up an electron, that means there's nothing that can then take an electron. And we know something needs to take it. And I just want to hit on this again. I know you guys got this in class, but you need to know that the reactants go to the products. And the direction of the arrow would change that. So if this arrow, if we had one arrow and it was going that way, the reactants would not still be on this side. They would need to be over here because the reactants go to the products. If you see a double-headed arrow or an arrow, two arrows on top of each other pointing in opposite directions, that means the reaction can be reversible. So it can go from reactants to products, but then it goes back from products back to reactants. And these are just some examples of reactions that happen in biology. We did that. The only thing then we need to talk about is the activation energy and catalysts. So again, on energy, you need energy to do everything. Chemical reactions, they all need energy. The amount of energy needed to start a chemical reaction is called activation energy. Sometimes this is really high and there's not enough. Again, we can't create energy, so the reaction needs to find it somewhere. If there's not enough energy for them to find, you can have a catalyst and it lowers the activation energy and speeds up the chemical reaction. If you have a reaction happening in a beaker and you add a catalyst, that's the chemistry sense. If we have reactions happening in your body, you add an enzyme. An enzyme is the same thing as a catalyst, but it's a protein. It's a biological catalyst. So an enzyme is a protein that increases the rate of reactions by lowering the activation energy. So if you lower the amount of energy needed, you need less to have it happen. And that will then leave you with more energy to do other things. Or you could store it and save it for later. Okay, that's it. Have a good day, guys.